Hello everyone and welcome to week 6 of Poll 361. This week we'll be discussing concepts, types, and limitations of sampling. Sampling is extraordinarily important to the research process because, as we will discuss in this lecture, it's almost always impossible to collect data on every single element of our population of interest. So instead, we have to rely on samples. And in this week's lecture, we're going to discuss critical components of sampling, such as sample size, discuss how we can have valid and reliable estimates of sample sizes of just a few thousand people, and how we can be confident that that is in fact representative of the attitudes of millions of people. We'll discuss in detail what a sample is, different methodologies for collecting samples, and we'll also discuss briefly some measures of confidence for our samples and some preliminary statistical inferences that we can make with samples. So before we begin, there are 3 specific terms that I'd like to highlight and define before we move on, because we're going to be using these terms a lot throughout the lecture. So the population is any well-defined unit of analysis. It's really that thing that we are trying to study. And generally these are, geographical entities or people. So things like states, counties, countries, or individuals. It's the population of interest that we are trying to measure and to study and to understand. And like I just said, because it's often very difficult, if not impossible, to completely measure or observe every single individual or every single unit of the population, sampling is required. Sampling is a subset of units collected to represent the entire population. And altogether, once we have our samples collected, then we rely on sample statistics, used to estimate the population values or parameters, typically through the usage of percentages or averages. So this week is just a deep dive into sampling, how it works, areas of bias that we need to avoid, and how we can make sure that we're making valid and reliable inferences from our samples. So just to highlight the differences of populations and samples with a few examples, let's say we were interested in researching how Americans' opinions on universal health care changed after the implementation of the Affordable Care Act. So here, the unit of analysis, the thing that we are interested in, is individual people, specifically the entire American population. We want to understand how Americans' opinions changed after the implementation of a specific policy. So the population that's needed for our survey, or the population that we're trying to measure, that's all American adults, about 300 million people. Since that's completely unfeasible, the next step that the researcher has before them is to obtain a sample of that population, okay? Let's do another example. Do high school students who study more have higher grades? Well, the unit of analysis here is students. That is the level or entity at which all of our observations are being made. Is it feasible to interview every single high school student in the United States? No, it's very clearly not possible. It would require so much money and time and resources. It's just not possible. So we have to rely on samples. We need to think of some way that we can effectively represent everybody in the population through a sample. And finally, how did the Affordable Medical School Initiative in London affect graduation rates for nurse practitioners? So here again, the unit of analysis is students, but the research question is very specific. It's students in nursing, and our population of interest is also hyper-specific. It's nurse practitioners who've recently graduated in London, England. So this might be a little bit more feasible just because the parameters of the population are so specific from the research question, but still, we could still have great difficulty trying to interview absolutely everyone that's in that population of interest for our study. And another thing that's you have to keep in mind here is that, yes, we can narrow the research questions so much that it does become increasingly more likely that you could interview almost everyone in that population, but then we run into generalizability concerns. So yes, you are studying this very specific initiative in one very specific location out of the entire world. What can this tell us about similar initiatives that are maybe conducted elsewhere in the world? Maybe not so much, because the case is so specific. So there are trade-offs, right? You can have a very narrow question, and that can allow you to actually engage with more individuals of that population. But at what expense are you, seeking that goal at the expense of the extent to which you can make generalizability claims to the broader population? So nurse practitioners, globally, for example. So as you have perhaps gathered by now, samples estimate the population. I have to reiterate this over and over and over again, because later in the semester, when we start talking about different statistical equations and inferences, there are very specific equations that you use for population parameters or sample parameters. So it's very important to understand now that in most cases, the true population parameters are almost always unknown, because we can't interview every person or conduct public opinion surveys for every individual in every state, in every country. We don't have perfect data from every single country that we might want to be making an analysis on. So it's very important just to realize now early that the population parameters, generally unknown. So what we have to do is we have to take samples from the population of interest to make inferences about those true population parameters. Now let's talk about 3 fundamental concepts regarding sampling that you need to be aware of. So the first is an element. It's a single occurrence, realization, or instant of the object that is being studied. Another way of thinking about this is that it is the unit of analysis. The element is the unit of analysis. Think of it like the row. Each of the rows in your data set, that is an element. Stratum is a subgroup of a population that shares one or more characteristics. And then finally, our sampling frame is the frame or method by which a sample is drawn from a population of interest. So let's take each of these in a little bit more detail. Okay, so one thing that I would like you to keep in mind is that a population, your population of interest, is really just a collection of elements, lots of different observations. So let's take these research questions one by one and discuss the element of that population. So imagine this research question. Do challengers sponsor more negative campaign advertisements than, incumbents, for example? So in this research question, the population element would be all campaign advertisements, and we would have a variety of other variables that we code alongside each of those campaign advertisements. So we would have a variable for whether that advertisement was positive or whether it was negative. We would have a variable that denoted the type of candidate that sponsored that advertisement. Was it a challenger? Was it an incumbent, right? And so on and so forth. So there, our element is all campaign advertisements. Research question number 2. Do people live longer in countries with universal health care? Here, the population element is every human being on Earth, because we are interested in determining whether or not people, the unit of analysis, whether their longevity, that's the dependent variable, is impacted by whether or not they live in a country that has universal health care. So obviously this one is extraordinarily unrealistic to measure. There's no way we could conduct a survey that interviewed every single human on the face of the planet, right? So definitely need sampling here. And then research question number 3. Was the United States Congress more productive after 9/11? Here, the population element would be all bills or all legislation that passed after 9/11. This one might be a little bit more feasible to write on. Congress doesn't pass that many laws each year, but nonetheless, the population element here would be all bills passed after 9/11. So those are the elements. Again, think of them like the rows in your data set. Those are your sample elements. Populations may also be stratified or subdivided or broken up into groups. So let's go through the previous examples and talk about how each of those elements might also be stratified. So campaign advertisements, for example, they might be stratified by emotional tone, so fear, anger, enthusiasm, and pride. Those might be meaningful groups of advertisements that we want to investigate. The research question 2, where every human being on Earth was the population element. People are obviously stratified by a variety of subgroups like race, gender, ethnicity, etc. And then our final research question, all legislation past 2001. Legislation could obviously be stratified by topic. That's a good example. So maybe bills that focus on national security versus redistributive politics or education. So a variety of topics that could kind of group different types of legislation. So stratum is a really key consideration when we're determining how we want to sample the population of interest. We have to take stratum into account. And really, what you might be noticing is that stratum is another way of thinking about our independent variables in our research. They are the other kind of factors that we think might explain differences between our observations. Finally, we have the sampling frame, and this is the particular population from which a sample is actually drawn. The sampling frame refers to the method by which we gather our sample. And I know that might sound a little confusing, so let's go through some examples. Let's start with example number 1. Let's say Dr. Rogel wants to interview community members about a city initiative to build more bike lanes. So, the sampling frame that Dr. Rogel uses, she randomly interviews every 1 out of 5 patrons entering a local shopping market. And you might think that this sounds fine, like, okay, it's random. I guess that means that's representative, right? But not necessarily. Imagine that she's at, a really high-end organic shopping market, right? And everything is overpriced, everything's organic, right? You're only going to get a very specific type of clientele that's going to that very specific shopping market. One key thing about making sure that our samples are in fact random and representative is that we have to ensure that every individual from the population of interest has an equal chance of being selected. So this would only be an appropriate sampling frame if this was a super small town that had like maybe 5 people in it, and it was the shopping market that every single individual went to, and they all happened to be there at the same time that Dr. Rogel was present. Otherwise, we see lots of potential for bias with this specific sampling frame. Let's take number 2. Dr. Quaid wants to gauge public opinion in a local mayoral race. So what is his sampling frame? The researcher distributes a mailer to 1,000 random households containing a survey. So you might be thinking to yourself, okay, well, the sample size is 1,000. That's pretty good. As we'll talk about later, that's an adequate sample size to be representative. He sent it to random households. I don't really see any issues with this particular sampling frame. And as we'll discuss in the survey and experiments chapter, I think next week or in 2 weeks, one issue we have to consider here is that we're probably going to get a significant number of people who return the mailer that are really interested in the mayoral race, that are really opinionated, they're probably really polarized, and they probably have a lot to say. Those are the people who are, going to take their own time to fill out the mailer, find a stamp, go to the post office, and actually mail it. People who are really passionate about politics anyway. The average person would probably say, no, I don't have time for this, and throw it away. So there's some potential for bias with this sampling frame as well. Let's take the third example. Dr. Bowen wants to know how people feel about recent congressional legislation to ban assault rifles. And here, in this case, Dr. Bowen, she randomly dials numbers from the phone book to gather opinion data on gun control. Any potential issues with this? Well, this is generally the way that most public opinion polls are conducted today. Random digit dial, everybody has an equal chance of being selected, and it's completely random. One potential issue, when we talk about millennials and Gen Z, they generally don't have landline phone numbers, so it can be a little difficult to make sure that you're reaching that specific stratum of a population, these younger individuals who don't have landlines. But otherwise, this continues to be the main way that samples are conducted or gathered, collected. So the third one, this might be the least biased of all of the sampling frames presented here. And so we've been talking a lot about bias and sampling bias, so I just wanted to give you the textbook definition of that to prepare for your midterm examination. Sampling bias is systematic error due to a non-random sample of a population, causing some members of the population to be less likely to be included than others, resulting in a biased sample. So each of the in-depth kind of breakdowns or critiques that I just gave of those previous sampling frames, those are all examples of sampling bias or potentials for sampling bias. So be aware of those. You will see some questions on the exam that, presents a sampling frame or, a research methodological approach, and you will be asked to critique that approach for any potential bias. So how do we actually collect samples? What are some approaches that we can use to collect samples of populations of interest and do our best to minimize bias? Well, there are two basic types of samples, and lots of little examples within each one, of course, but the two main types of ways for collecting samples are either through a probability sample, or a non-probability sample. And as you can see, based upon the bolded words here, the difference is between whether or not we have a known or an unknown probability of having a specific individual included in that sample, or case, or country, or whatever the population element is. There's 4 types of probability samples that I would like you to be aware of: simple random samples, systematic samples, stratified samples, and cluster samples. So let's take each of these in a little bit more detail. Simple random samples are samples in which each element in the total population has an equal chance of being included in the sample. So what would this look like exactly? Well, let's say that you wanted to write a research paper on the 10 richest countries in the world, but your professor tells you that you can only analyze like 5 distinct cases or something. So you have to ask yourself, okay, well, how do I choose the 5 random countries out of this list of 10 that I'd want to analyze? And really, this is pretty simple, right? You could gather your list of cases. So your population of interest would be the 10 richest countries in the world. So you'd go to some database and you would find, or a news article, right? And you would find this list of 10 countries. And you say, okay, I need to find a way to randomly extract 5 of these, and these are going to be the ones that I write about. And you could go to some random number generator website on Google, and you could say, randomly pick a number between 1 and 10, and say it spits out 5 distinct numbers: 7, 1, 6, 2, and 10, and that would correspond to the numerical value that you had given each of your cases. So you would end up analyzing Norway, Qatar, Ireland, Macau, and Switzerland, okay? And this is really helpful because some of you have public opinion data that has, like 3,000 observations in it. For some reason, you may need to lower your number of cases if there was some reason for doing so. And, I will teach you guys how to do this later in the semester, but we can tell different statistical software programs to randomize cases and only keep like 100 observations or 500 observations, for example. But this is really helpful if you find yourself in a case where you need to conduct research. The number of cases in the population is really high, and you need to randomize and create a sample. I actually did this for my most recent research project, where I had to do a content analysis of emotional tone in campaign advertisements, and there were over, I think, 50,000 campaign advertisements that I could have potentially watched, and that was unfeasible, right? I didn't have enough time or resources to do that. So, I went into computer program and I said, randomly give me 1,200 of these instead. And that was my sample that I ended up analyzing in my research project. The next type of probability sample is a systematic sample, and it's a little similar, but it, as the name suggests, is a little bit more systematic. So systematic samples are random samples that are derived systematically, typically from a manifest or a list of elements, and the sampling interval represents the randomization process. So say we had a research project where we had to analyze certain characteristics of a subsample of presidents since Teddy Roosevelt. And we had to make a determination on which presidents we were going to analyze, but we wanted to make sure that that randomization process was at least systematic. How would we do that? Well, the sampling interval is an equation that we can use to make sure that we are randomly sampling from our population of interest in a non-biased way. And the sampling interval is represented by the equation K, which stands for the sampling interval, equals uppercase N, which this is a good opportunity to familiarize yourself with this. Uppercase N refers to the number of observations in the population, divided by lowercase n, which represents your desired number of cases or your sample number of cases. So just remember, uppercase N equals observations in the population, lowercase n equals number of observations in your sample. This is going to come in handy a lot later in the semester. So out of this list of 20 presidents, say we only had time to analyze 5 of them. How could we make sure that we systematically sampled from this list? Well, we would just input our appropriate numbers into the sampling interval equation. So 20 is the population, the number of population observations, divided by 5, which is our desired sample size. And 20 divided by 5 equals 4, so we could just move in a really systematic way where we pick every 4th observation from the list, and ultimately that constitutes our sampling size. So we could start at the very top, or we could start randomly anywhere in the list. Say we just started randomly and we ended up on Gerald Ford. Now what we're going to do is we're going to use our sampling interval and we're going to pick every 4th observation. So we would start with Gerald Ford. We would get Dwight Eisenhower. After that one, we'd move down 1, 2, 3, 4. We'd get Calvin Coolidge, and we'd move down 4 more times, 1, 2, 3, 4. Ended up with Teddy Roosevelt. And then one more time, 1, 2, 3, 4, end up with Bill Clinton. So generally, in my opinion, I think it's always a good idea to just go with a, traditional, simple, random sample. There might be some theoretical reason why you would want to move in a systematic process like this. So at any rate, these are just 2 examples of how to draw random observations out of a population of interest. In most cases, I think the simple random sample is probably what you would want to use if you needed to randomize from a specific list of, population observations. But at any rate, these are just the differences between the two. Stratified samples are perhaps what's used most frequently in the social sciences. They are probability samples in which elements sharing one or more characteristics are grouped, and elements are selected from each group in proportion to the group's representation in the total population. And I apologize for that horrible definition. It's the one that's used in your textbook, but let's try and make this a little bit easier to understand. So I've got a few examples for you that I think will really clarify why we might be interested in stratifying our samples. One thing that I want to point out here is that stratified samples are really important when we have very heterogeneous populations. So I have two pie graphs here for you, and I want to point out the difference between a population that's largely homogeneous and a population that's largely heterogeneous. So homogeneous or homogeneity means that those things are, it's talking about sameness, right? We can see from our homogeneous population that trait 1 constitutes almost the entire population, so it's not very diverse, okay? So if we were to take a random sample from this homogeneous population, most of those elements would probably have trait 1, and that would be okay because that is representative of the entire population itself. On the other hand, when we're dealing with more heterogeneous populations, in other words, there's a lot of diversity, lots of different traits that are in that population that we're interested in studying, then we might want to take extra care to stratify that sample so we make sure that each of these different traits are represented in our sample. And I hope that makes sense. And if it doesn't, as always, just be sure to post your questions in the discussion board. Let's go through some examples to help clarify these concepts and why stratified samples and maintaining these heterogeneous traits are important. So let's start with a really kind of silly abstract example for starters. Let's say that we had a population of 500 colored balls, and we wanted to sample 100 of those. But since there are so many different colors, we want to make sure that we have a representative amount of colored balls from each of the possible outcomes. So the first thing that we do is we obtain the sampling fraction. That's denoted here by sampling fraction equals lowercase n, so the desired sample size, divided by n, the total population size. So it's completely flipped from the sampling interval. So as we just said, the desired sample size is 100. The total population here is 500 colored balls. So we take the desired sample of 100 and we divide that by 500, the total population, and we end up with 1/5 or 0.20. And one way to think about this is that there's 500 colored balls. We don't have enough time or resources to meticulously analyze all 500. We want to analyze 100. So essentially, we are moving from 500 observations to 100 observations, but we want to maintain the distribution of the population. So that's why we take the n from each category, and we're going to multiply that times 1/5 or 0.20. That way we can maintain the integrity of the proportion of each group, but in just a much smaller, manageable size. And this is the essence of a proportionate sample. We have only changed the number of observations that we're analyzing, but we have maintained the integrity of the characteristics of each group. And that might still be a little bit abstract because it is a very abstract example from your book. So let me just do one more to help you kind of understand stratified samples, specifically with a proportionate sample. And a really good example is, imagine that you find a recipe for cookies on the internet, but it's you know, it's a recipe for like 4 dozen cookies or something like that. And you're like, oh my God, I so don't need 4 dozen cookies just laying around my house. So you see the recipe, it calls for 3 sticks of butter, 2 cups brown sugar, etc., etc. It's a ton of ingredients. And you say to yourself, well, I don't have 3 sticks of butter or 2 cups of brown sugar. You know, I don't have that much of these ingredients, but I do have half of everything. So in a way, we want to stratify these ingredients to be smaller in their sample size, but we still want to pay particular attention to the proportion of each of the ingredients. So what we do is we just divide everything in half. And this is essentially what we just did in the previous example, except we did it by 1/5. So instead of 3 sticks of butter, we've got 1.5 sticks of butter. And you can go all the way down the list and see that we've just halved everything. So I hope that maybe that helps clarify, you know, the purpose of stratifying a sample, and with the specific purpose of making sure that all of the, you know, ingredients or elements maintain their distinct proportions. Okay, so now that you have a pretty good understanding of proportional samples, now I want to introduce the concept of disproportionate samples and talk about when and why you might want to use a disproportionate sample as opposed to a proportional sample. So let's imagine that we wanted to analyze student performance at a local college. And for the sake of simplicity, let's say that there were a total of 3 different majors that students could choose: liberal arts, engineering, or business. We can see from this graph here that there's a total of 800 students. But again, let's imagine, based upon our time and our resources, that we only have enough time to interview 200 students. And since we're very interested in the type of college major, and we know that the population is stratified this way by major, that's a very integral component, we need to determine whether a proportionate or disproportionate sample is most appropriate. So let's do a recap of proportionate samples and see if this would be an appropriate method for sampling for this specific population. So first we would calculate the sampling fraction. Remember, this is the desired N, which would be 200, and we would divide that by the population size, which we add up 500, 200, 100, that's 800. And this would produce a sampling frame of 1/4. So 200 divided by 800, that would equal 0.25. That is our sampling fraction. So we would want to multiply each of these groups by 0.25, and that would produce a perfectly representative but smaller sampling of college majors. And again, imagine it's like the cookie recipe. We just need smaller proportions of all of the elements or the ingredients. So 500 times 0.25, that equals 125. 200 times 0.25, that equals 50. 100 times 0.25, that equals 25. So here on the right-hand side, you see our perfect proportionate sample that meets our threshold, our criteria of a sample size of 200. So what I want to ask you is, do you think that there's anything wrong with this approach? It's perfectly representative. It meets our criteria of a 200 observational sample. Is there any potential for bias here? Well, think back to a few slides ago when we discussed the difference between homogeneous and heterogeneous populations. And there's no hard or fast rules here. It's kind of, all of this is really up to the researcher themselves, but there's a few points that I want to emphasize here. Generally, when there is not a whole lot of diversity in the attributes of a population that you are examining, you can probably get a pretty accurate sample of that data just by simple random sampling. However, when your population is pretty diverse and there are many attributes or strata that you're interested in studying that you think are relevant or pertinent to the dependent variable, the thing that you're trying to study, it's probably a really good idea to make sure that you stratify that data in some type of way that preserves the components of each of those groups. You want to take extra steps to ensure that all of your different groups in the population are being accurately represented in your sample. And this is generally done through disproportionate sampling. And again, there's no specific number or threshold or rule for determining whether or not you should use a proportionate or disproportionate sampling method. Again, it's pretty much a judgment call, but I think for the purposes of this class, say if 80% or more of all of your cases share the same exact attribute, then statistically speaking, simple random samples would probably suffice. And if we return to our case here, we can see that this, in fact, is actually a pretty heterogeneous sample. There's a lot of diversity here when it comes to college major, and no single major here constitutes more than 80% of all of the cases. So it's definitely not a homogeneous population that we're dealing with. And for reasons that will be made more clear later in the semester, it's also highly problematic that one of our categories only has 25 observations. Generally, if, strata and groups are really important to our research question, we want to have at minimum 30 observations or cases per group. Ideally, we would have 50, but at least 30. So this is a great example here of why we might need to use a disproportionate sample, because we have very little engineering majors in the perfectly representative proportional sample that we used. So what can we do to increase the number of engineering majors in our sample? And this is where a disproportionate sample comes in. As the researcher, you have to make the judgment call and justify why you did what you did in your specific research papers. I don't think that this is going to apply to anyone in this class anyway, but if you continue, to conduct your own data analyses and things like that, like this is 100% an issue that you'll run into. I've had to use disproportionate samples for my research on campaign advertisements all the time. For instance, I'm really interested in discussing attack advertisements and different types of strata within attack advertisements, but generally in a given election year, anywhere from like 20 to 30% of all advertisements are even negative or like attack advertisements in general. So I always have to stratify my samples to make sure that I have enough observations of my pure attack ads to make genuine statistical inferences with. But at any rate, what we could do is we could simply just cut down the number of liberal arts majors. We could cut that down to 100, and then we could have 50 majors each from the two remaining of our majors left. And this would be enough for us to hit our desired sample size of 200. It's pretty arbitrary, but it's just up to the researcher to decide how many cases might need to be in each strata if you're using a disproportionate sample. And now that we've got 100 liberal arts majors, 50 engineering majors, and 50 business majors, now we have enough observations per group to make meaningful statistical inferences. But there's one more step involved. If you ever use a disproportionate sampling method, this is one thing that you absolutely have to keep in mind, and that has to deal with weighting. WEIGHTING, weighting your variables of interest. So take a look at this graph that we have now, this pie graph of our new disproportionate sample that meets our criteria of a desired sample size of 200. Now the sample is biased towards engineering majors because they are way more overrepresented than they are in the true population. And now liberal arts majors are underrepresented. And since the whole purpose of this, hypothetical research question was to gauge student performance, and one way of doing that is through GPA, imagine also imagine this is like well documented in the literature, right? That engineering majors on average tend to have really high GPAs than any other major. And so this disproportionate sample is going to inflate a GPA that is not truly representative of the entire population. So I hope that makes sense. I'm going to go ahead and end part 1 right here. And when we start part 2, we're going to jump right into how to weight variables in our data.